The horizontal component is nothing but mg sine theta. So this will be the action, but this will be the reaction of it. We have got three types of damping. So which are those? It is light damping, heavy damping, and critical damping. The system which oscillates with its own natural frequency is said to be a free oscillations. Hello everyone, I'm Brinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 3 of chapter 14, and chapter name is Oscillations. In previous class, we had studied regarding the expression for oscillations of spring. That was vertical motion, that is a vertical oscillation. Now we have got the horizontal oscillation, and we study about the expression for oscillations of what it is a simple pendulum. So as you all know, what is meant by a simple pendulum? You have seen in a pendulum clock and all. So it is just the extension, that is, suppose you consider a thread which is fixed at the surface as shown in the figure. So consider this is the one which is fixed. So let me tell this point as S. So I am calling this point as S, where exactly the cotton thread is fixed, and below the cotton thread there is a presence of a bob like this. Okay, so that is given an oscillation. You can see a pendulum clock, it undergoes like horizontal oscillation. As the bob is suspended, the bob is allowed to move, that is it is allowed to have the to and fro movement, that is the oscillations. So when that is the case, here there is a tension which is created along the string, and it is given by this arrow mark, and it is mentioned as T. Okay, so S is a fixed position and length of the string is said to be L. As it moves towards the other direction, it makes an angle theta. Okay, and the tension which is created along the string is said to be T. Okay, and what is this mg? Mg is the force which is exerted downwards, and g is acceleration due to gravity of this bob. So it forms two rectangular components. So what are those rectangular components? By what is it representing rectangular components? Because it is making a certain angle with the help of this bob. So what we get along S, and let me consider this point as A. So along SA we have mg cos theta, and the perpendicular to this SA we have mg sin theta, which makes a rectangular component. So now what is our aim is to derive the expression for oscillations. So oscillations of what? It is simple pendulum. So when that is the case, as I told you in the previous session, what we have done, we have derived the expression for the time period in order to check for the oscillations, and we have got the expression for the frequency. Similar way in today's class also, that is under this topic, we are going to study regarding the expression for oscillations of this apparatus, and that is simple pendulum. So first of all, you will have to consider the component which is horizontal. Okay, so the horizontal component is nothing but mg sine theta. So this will be the action, but this will be the reaction of it. So this is a restoring force. It is getting restored back to its original position, and again if this undergoes action, it will be like this. So it is just moving to and fro movement, but this is the mean position. These dotted lines represents mean position of the simple pendulum, where at this position the velocity is 0. Okay, so that will be the origin from where exactly it starts. So we consider the perpendicular component. On considering perpendicular force component, we have got F is equal to minus mg, and it is along this direction, that is sine theta we are taking, and negative because it is the restoring angle, restoring force. Okay, so it is minus mg sine theta. Since Sine theta is approximately equal to theta. It is small, that is why we approximate it to just theta. So our equation becomes F is equal to minus mg and theta. So we know that according to Newton's second law, we have F is equal to m into A. So what happens? We have A is equal to F divided by m. So we can write this as F by m is equal to minus g theta. Let me consider this as acceleration. So A is equal to F by m minus g theta, and we know that theta is nothing but, that is, the displacement is nothing but, what is the displacement which is taking place here? Along with the length, you have this theta. The length makes an angle theta, that is nothing but the displacement. Okay, so you can give this as g into, instead of theta, I can just take it as x divided by L. So I'll just take it as x by L. And we know that for SHM, acceleration is given as minus omega square. Actually, it was minus omega square. Why? Because it was for the spring in y direction, that is vertical direction. Since it is moving in horizontal direction, this is in x scale. So I just consider the other term as x, minus omega square x. So on equating this equation, equation 1 and this equation 2, we have minus omega square x is equal to minus g x divided by L. Minus minus cancels, x and x cancel. So what remain is omega is equal to root of g divided by L, and we know that omega is given by 2 pi divided by the time period t. So I can substitute, let this be equation 3 and let this be equation 4. Substituting equation 4 in 3. So I substitute my equation 4 in 3. What do I get? It is like 2 pi divided by t is equal to root of g divided by L. What remains is like t is equal to 2 pi root of L divided by g. So this is said to be the time period, that is, how do you determine the oscillations of the simple pendulum? Is by determining the time period equation for a simple pendulum. And finally, you have received this time period of a simple pendulum. If you want to have the frequency, it will be reciprocal of this time period equation, which will be 1 divided by 2 pi root of g divided by L. That will be the equation for, that is the frequency, reciprocal of the time period. So that is all about your oscillations of simple pendulum. After equating, after all the expressions, what are you supposed to do? What is t here? T is the time period, L is the length, suspended length, and g will be the acceleration due to gravity. That is how you will have to name the terms of the expression. So that's all about your oscillations equation, and now we are moving to the damped oscillation. This is the last part of the chapter, that is chapter 14, oscillations. So what is meant by damped oscillations? What is the damping? Damping means nothing but, however you give certain vibrations to an object, the object undergoes vibration. So is it that the object continues to vibrate? It doesn't stop at all? No. Each and every vibrations or each and every actions are having certain stop. Okay, so it comes to rest. That is like during walking motion or rolling motion or something, the friction is the one which is necessary for it to get into rest. That is, the initial whatever speed was there, when it comes to final, the speed decreases. Similar way, here it is called as damping of the oscillations. That is, the frequency through which it vibrates, finally it comes to rest. How does it come to rest? It decreases. It maintains certain frequency, it keeps on moving, and finally it gets feeble. After it's getting feeble, what happens? It reduces. The reduce completely towards the rest position of the vibrations. Okay, the same way it goes here. That is, if the amplitude of the simple harmonic motion, as I told you, what is meant by simple harmonic motion? It is nothing but the vibrations of the object where it undergoes oscillations, and when it undergoes oscillations, its amplitude as well as the frequency both remains constant. Such kind of a motion of a particle is said to undergo a simple harmonic motion. Okay, so here the amplitude of such kind of a simple harmonic motion, it varies. That means it decreases with time and finally it dies out. So then it comes to its rest position. Then such kind of a oscillation is known as damped oscillation. So damping causes reduction in the amplitude. So suppose you have got your amplitude, it starts reducing and it stops. Okay, so here this is kind of a damped oscillation where further amplitude is not seen. Okay, so we have got three types of damping. So which are those? It is light damping, heavy damping, and critical damping. So what is meant by this light damping, heavy damping, and critical damping? So as we all know, the light damping is the damping that is oscillate. What happens in damping? It is like the frequency decreases. So once you give the oscillations to any object to come back to its equilibrium position, it takes a longer and longer time. Such kind of a damping is known as light damping. Heavy damping in the sense there is no such oscillation motion for an object which is given, but once the motion is given, it comes back to its equilibrium position. Okay, but in order to come back to its equilibrium position, again like the light damping, it takes time to come back to its original position. Next, it is all about the critical damping. So what exactly happens in the critical damping? In the sense, the critical damping, the oscillations is given to the object. The thing is, it doesn't overshoot back. Okay, so there is no such oscillations which it undergoes, and it comes back to its equilibrium position very quickly but doesn't overshoot back again. So having these three types of damping, let us introduce some real life examples under this along with its definition. So you have got in the slide, that is, see, you can see a girl is swinging over there. So swinging is an example for the light damping. Swinging can be taken as a common example for damping oscillation or a damped oscillations. Okay, but under damped oscillations, if you have got three types of damping, that is light, critical, and heavy, then you will have to know that for which example this swinging concept belong to. Okay, so that is all about the light damping. So what happens? You have observed, you just push your friend in the swing and you just leave it aside. What happens? Until and unless you exert certain external force by pushing with the help of your leg, the damping is always present in the swing. Okay, so we have got like light damping, the oscillation gradually decreases in the amplitude but takes a longer time to stop. So if you don't give any external force or the pressure on the swing, what happens? It takes a little bit of longer time in order to come back to its equilibrium position. And next it will be critical damping. So what exactly happens in critical damping? You can see here the meter. In vehicles, you can see the speedometer is there. No, that is an example for this critical damping, in that the system returns to equilibrium position here quickly without overshooting. I have told you it comes back to its equilibrium position, and that equilibrium position will be this 0. Okay, but it doesn't overshoot back. If it overshoots back, it will confuse the driver who is driving the vehicle. That is why it is made that it shouldn't overshoot back, and which is an example for the critical damping. Heavy damping is same as that of the light damping. It takes time for it to come to its equilibrium position, but here the system does not oscillate. Okay, remember, the system doesn't oscillate. You can see nowadays, you can see the doors lock will be like this automatic lock. Okay, so whenever you just just push it. It is just that you're giving motion to the door and you just leave it and come. It is not necessary that you have to turn back and close the door, okay? It itself will close the door by itself, but the thing is, it takes a longer time to come back to its original position, that is the equilibrium position. So that's all about the damped oscillation. And finally, we are into oscillations, that is free oscillation, forced oscillation, as well as resonance topic. So this will be the last topic which will be discussed under this chapter. Now we have free oscillations. That means the system which oscillates with its own natural frequency is said to be a free oscillations. Okay, so it has got its natural frequency. So such kind of oscillations with certain natural frequency is said to be free oscillation. Next we have forced oscillation. So what is meant by a forced oscillations? It is nothing but when a body is maintained at a state of oscillations by an external periodic force of certain frequency other than natural frequency of the body is being given, then the oscillations are said to be the forced oscillations. So a system will always possess a natural frequency, and along with this natural frequency, when an external force is applied on a system, it undergoes with the external frequency, which is also called as forced frequency. Okay, so this is all about the forced oscillation, which produces a forced frequency along with the natural frequency for a system. Such kind of one oscillation is known as forced oscillations. And finally, we have chord resonance. So what is meant by a resonance? Resonance means a phenomena in which an external force or vibrating system forces another system to have a amplitude and specified frequency. Such kind of a force is termed as resonance. So in today's class, we have discussed about the expression of oscillation of simple pendulum, what is meant by damping under the concept damped oscillations. So there are three types of damping: light damping, heavy damping, critical damping. Along with that, we had studied about free oscillations, forced oscillations, and what is meant by resonance. So these are just 1 mark questions which is important, that's all. So here ends our chapter 14, that is oscillations. Let us all meet in our next class with the upcoming sessions. Until then, have a good day. Thank you.